Hello everyone, and welcome back to another lecture video for the course of Database Design and Implementation. So to quickly go over the topics that we have covered up until now. Up until the last lecture, we had discussed about data models and the importance of data modeling. Herein, we talked about how data models helps to provide a standardized view of the data storage and processing requirements from different entities involved in your organization. We also learned about the different basic building blocks of our data models, right? We learned about what do we mean by an entity, an attribute, relationship, and the different relationship types, which were 1:m, 1:1, and the logical m:(n), right? And then constraints, which will basically help us together with these basic building blocks and a data model of our choosing, we will be able to convey the conceptual design of our database to everyone. Okay, and thereafter we discussed about the different types of data models, right? So we looked into the very first one, which is basically the hierarchical model, and then the network model, and then the relational model, the entity relationship model, and then the object-oriented model, the XML model, and then the NoSQL model, so on and so forth, right? And then finally, we learned about the different models that helps us realize the database design and implementation process. If you remember, the design and implementation process, as discussed in the earlier videos, can be encapsulated by 3 design steps, right? So one, you had the conceptual design, then you had the logical design, and then you had the physical design. So for each of these design steps, there are some corresponding data models or corresponding models that you will have to use or develop, right? And we learned in this chapter of data modeling that conceptual design can be represented by using the external model and then the conceptual model. And then the logical design can be done by using the internal model. And then for the physical design, we have the physical model. And we summarize this chapter with the different steps that we will have to undertake in order to design a database from scratch, then express its schema or its blueprint, which is the conceptual design, implement it using a particular database management system or a software, and then finally, optionally speaking, if you would like to account for its physical design, then you can also do that. But that is outside the scope of this particular course, right? So we will be restricting our discussions typically to the conceptual design and the logical design. So moving forward, the agenda for this lecture, and of course, we will also wrap it with the goal of the next few lectures that we will have, is to identify specific data models and discuss them in depth. So if you recall, a part of our discussion from the last lecture was the fact that we said that for this course, as far as database design is concerned, as well as implementation, we would be using what is known as the relational model or the relational data model, right? Where the relational model, compared to its predecessors, which were the hierarchical model and the network model, relies on the logical simplicity of data. Instead of worrying about the lower level details of how the data storage will be implemented on specific hardware platforms, the relational model focused more on how data can be represented, right? And how data should be represented. And that is what end users and developers should be more concerned about, rather than how exactly would it be implemented on a given hardware platform, right? So our goal is to first, in order to simplify the logical representation of data, we would want to select the relational model. And then on top of that, in order to simplify the graphical representation of the aspects of the relational model, we will be learning about the entity relationship model. Okay. And then, if applicable, we will be applying the concepts of object-oriented programming in the form of attribute inheritance and abstraction, and then apply the extended or the enhanced entity relationship model. And then we will supplement this whole design process with the techniques of normalization in order to make sure that the final design that we have generated by using these three data models is as robust as possible. So in the upcoming few lecture videos and the next 2 or 3 weeks, this is the overall agenda of our lecture videos, right? We will be discussing the structure or the different components of this model and how they operate for all these three models. And then we will be learning about the techniques in order to transform a specific database design from lower normal forms to higher normal forms, such that we can minimize as much as possible the existence of data redundancy in our database designs, right? And as a result of that, avoid all the issues that file systems used to face in the form of data anomalies. Okay. So in this lecture, we will take the first data model that we are concerned of, and we will discuss that. So we will talk about the relational data model. Okay. And we will discuss about the concepts, a mathematical concept known as functional dependency. And how, using this math concept, we can implement what is known as the concept of keys in databases. Okay, and we will learn about the different types of keys and what is the importance of having a key in a database. Okay, and thereafter we will learn some integrity rules for the database environment. For any storage that is done within the database systems, these integrity rules must be preserved at any and all cost. So we're going to learn about what are these integrity rules and what needs to be preserved when it comes to these integrity rules. Okay, and thereafter we will discuss about some of the relational operators. Okay, so what are the different relational operators that helps us? So the specific purpose of these relational operators is to aid us with the transformation of stored data, right? So we will talk about these relational operators, and these relational operators also is a foundation to SQL, the structured query language that we use in order to formulate our queries and then transform the data, right? So we will conceptually understand these relational operators. What are the different relational operators that are available within the relational data model, and what is their functionality and how they work, right? And then we will probably end this particular topic with some relational algebra. So if you are not familiar with relational algebra, or if you have forgotten relational algebra from a bit from discrete math, then now would be the time to revise some of its basic concepts and kind of revitalize that knowledge that you might have had in this particular domain. Okay, but otherwise we will try to, as much as possible, reasonably possible, have a structured segue from the relational operators, understanding the concepts of the relational operators, and then going into the relational algebra. So as long as the prerequisites are concerned, if you have an understanding of logic, of how to formulate a logic to solve a specific problem in terms of developing a query, and then if you understand the concepts of the relational operators, then you don't need to have very in-depth knowledge about relational algebra as such, right? So you will be able to deal with it. But what is essential is that you be able to formulate a logic to solve a particular problem. So that means if I say that given a data storage, extract the first name and the last name of the students who have a GPA greater than 3.5, right? You should be able to express this logically by using the relational operators. So you should be able to understand that if you're trying to extract something, or if you're trying to fetch some data, how to formulate that step by step in an order such that you fetch the correct data, right? So as we go forward, you will see that it is to a certain degree straightforward. So as long as you're good with algorithmic design, right, you're able to formulate algorithms for different programming aspects, you should be able to deal with it. Okay. So how we are going to address this in terms of lecture videos is we're going to break this topics of discussion down into two particular videos. Okay. So the first one, we are essentially going to talk about functional dependencies, the different types of keys that are present in the database environment using the concept of functional dependency, and then talk about the integrity rules of the database environment. Okay, and thereafter in part 2, we will discuss mostly about the relational operators and relational algebra that are there in the database environment. In addition to that, relational data models also provide what are known as indexes. Okay, database indexes. So at this point of time, we are not going to go very in depth in indexes. There will be a separate chapter later on as we move forward after the implementation, after learning about SQL, where we will discuss it in a bit more in-depth fashion about what indexes are and what they help us to achieve, right? So at this point of time, I would just briefly touch over indexes and basically explain what indexes does. Okay. So later on, when we get to query optimization, we will discuss indexes in a more detailed fashion. So moving forward and getting to the first topic of this video, the motivation. Let's talk about the motivation of using the relational model. Okay, I'm going to stop saying relational data model all the time, but keep in mind that this is basically a data model. Okay, so the first thing that we have to keep in mind is that the relational model emphasizes on what is known as conceptual simplicity. And what this means is that the lower level details of the physical implementation of your data storage unit or data storage structure is kind of not required for end users and developers to be aware of, right? So similar to the concepts of object-oriented programming, where people introduce that for programming, everyone does not need to know how certain things are implemented. As long as they understand what they want to implement and know the particular methods that needs to be called, then that is good and okay, right? So that same concept is availed here as well, that given that you're only concerned about designing a data storage and then being able to process certain data in order to generate some specific set of information, you're not at the very beginning interested about how that thing will be implemented on a specific hardware platform, right? So that is where the motivation of relational model or developing the relational model comes from, right? So what it does is it is able to logically express the storage of data and its relationships. Okay. And it is also able to simplify and standardize the design process of the database. So this means that if we are freed up from the dependency of any particular hardware platform, so that means any kind of design that you generate for your database, it is applicable to any platform that you're going to implement. So you don't have to worry the specificities of those platforms. And that is going back to the same discussion of ensuring conceptual simplicity, right? So in order to do all this, it uses the mathematical concept which is known as relations, okay, which kind of expresses that the intersection of any column and any row is going to signify a specific data for that particular row and column. Okay, so that is the logic behind what relations are. All right, so that means from the perspective of end users and designers or application developers, right, or app developers, the focus will be on the end user interface and generic design of data storage. Okay, modeling real world interactions. All right, So once we understand this, before we move any forward, we have to discuss the generic structure or some of the properties of what is known as the relational table. Okay. So whatever data we are going to be storing is going to be stored in what is known as a relational table. And there are a certain set of properties of something, of a table, to be called relational. Okay. And that is what makes it different than those models like NoSQL models, which is basically schemaless, or it doesn't have any particular structure within that aspect. Okay. So these properties are as such. So any relational table is a two-dimensional structure with rows and columns. Okay. And thereafter, each row will represent a real-world object. Okay. Sometimes you will see that the nature of the tables that you design might not necessarily reflect a real-world object. But as long as you are trying to represent, or as long as you're representing from each row where the object can be a person, place, or a thing, then this property kind of holds. Okay. Each column will represent the properties of the objects stored. In the table, right? So basically attributes define the objects that you're storing in the particular table. Okay. The intersection of a row and column will represent a single data value. This part, or this property, is very important. Okay, you always have to keep this in mind. Thereafter, the next one, which is also very important, is all values of a specific column must have the same data type. Okay. This is also pretty important. Thereafter, each column will have a specific range of values for the data they store. And this specific range of values is also known as its attribute domain. And this is also very important. Okay. And thereafter, the final one is each relational table must have an attribute or a set of attributes which can uniquely identify every row in the table. Okay, so these are some of the properties of a relational table, and the last four that we have here are the ones that you need to kind of remember when you are interacting with a relational table going forward, right? So when you're going to be implementing these relational tables, you have to keep in mind that these properties are met. So some of these properties are the first, like the first threes are kind of like pretty straightforward. You don't have to really think about them. But beyond that, you have to ensure that all the last remaining properties are actually present for any relational table, right? That you cannot store multiple values in the intersection of a row and column, okay? And then you cannot have different data types for different values of a specific column. You have to keep that in mind, okay? And every column will have a specific range of data values, okay? And you cannot store values that are outside of this range. And then there must be an attribute or a set of attributes which allows you to uniquely identify each and every row that is stored or present in the table and kind of distinguish them from one another. Okay. So just a quick note is that sometimes this entire table, this entire relational table will be called an entity. Okay. And each row, sometimes a row will also be referred to as a tuple. Okay. And a specific row might also be referred to as an entity instance. Okay. However, we will be mostly using the term row to refer to the same thing, or it means the same thing. So we have to keep that in mind. And we might interchangeably use the term entity to either call a row or sometimes call a table. So we are basically overloading the keyword entity. Right? So please make sure that you don't confuse yourselves with the differences of what it is kind of representing in terms of its keywords, right? So that means if you want to put all of these properties into a perspective, okay, so that means if you have a table, let's say the example that we did in our discussions from a poorly designed database, right? So if you go back to that design and let's say we have something along the lines of student and the courses that they have enrolled in, right? So the attributes that we had were something along the lines of student ID, right? And then we had student Grizzly ID. Then we had student name, right? Then student GPA, okay? And let's say student department. And let's say student address. Something along these lines, right? And then you would have IDs like 001, 002, 003, and so on and so forth. And then Grizz ID being G123, G456, G789. And name could be anything, right? So we can say Thor, Odin, and look if they decided to join a university. And let's just give 3.56. He's the Allfather, so let's give him 3.99. And the trickster, let's just somehow make sure that he is always best in Thor. So 3.76, right? And the departments could be electrical engineering, right? And then philosophy. I don't know. What would Loki be? Let's just put him in ComSci, okay? Or CSI, ComSci and Information Technology. And address, well, they're all from Asgard, so, but now it's no longer there because of Thanos. So it could be anything, okay? So just give Auburn Hills, something like this, Rochester Hills, and Detroit. Something along these lines, okay? So now if we look at the properties that we had here, and let's try to look at each one of them, right? So it's a 2D structure with rows and columns. So here it is, a 2D structure. Where is my pointer? Here. So it's a 2D structure with rows and columns, okay? Thereafter, each row is going to represent a real-world object. So here, each row is representing a specific student information, okay? And then each column will basically represent the properties of the objects that they are stored. So for each student, the columns of student ID, student grizzly ID describe a specific property associated to the object that we are trying to store in this particular table, right? And then the intersection of a row or a column will represent a single data value. So that means the intersection of, let's say, this row and this column has a single data value. Okay, you remember, we cannot have data structures similar to that of an array or stack or something along those lines in a database. It is always a single value. This is very important to remember, that you cannot have multiple values within a data storage. You cannot write G123, comma, G456 in the single location. If that happens, then this is not a relational model or a relational table, right? So you have to keep this in mind. The next thing is, all values must have the same data type for a particular column. So this could be numeric, right? We can have this as numbers, and we can say 3, 0, okay? 0 stands for decimal, 3 stands for how many units do you have in the real part, okay? Or in the whole number part. And then GID could be alphanumeric, so you can have something like varchar 5, okay? Student ID will again be varchar, and so on and so forth. Varchar stands for variable characters, or any kind of string. You can think of varchar similar to that of strings in your programming language, and this could be decimal, and that will be 1, 2, and so on and so forth, right? But whatever it is that you select, all values must belong to that same or conform to the same data type, okay? And then the next property is there will be a specific range of values. So whenever you're going to be declaring this table and implementing them using SQL or the data definition language, you will have to specify what is the range of the values. So as you can see here, I am specifying the range of the values along with the data types of these attributes, right? So that means for this particular data type here, student GID, if I'm trying to enter a GID of 7890, then this will flag an error for the entry of this particular data record. And the reason behind that is when we were declaring this particular column within this table environment, we said that the number of characters that we can have is basically 0 to 5. So if you have any more than that, then it is going to throw an error. Okay. Of course, you can say that, hey, oh, this is 1, 2, 3, 4, 5. So what is the error? Well, you can add one more 0 here, and then it conforms to an example. The bottom line is it's an example. So that's what I was trying to express through this particular example. Not that in any case, in this particular setup, 7890 with a G will throw an error because it's just on the borderline. Okay, but you get the idea of what I'm trying to say. So similarly, if you here in decimal 1, 2, if you try to store 44.963, this is again going to flag an error because it kind of violates, although it is a decimal, it violates the attribute domain. So you have to keep that in mind. Okay, and then finally, there should be an attribute or a set of attributes that would be able to uniquely identify all the rows from each other and distinguish them from each other. So as a result of that, if you look at this particular table setup that you have in front of you right now, and if you say that, okay, what attribute or set of attributes can help me do that, then there are some attributes which does not help us achieve that. And then there are some attributes which does help us achieve that. So the attributes that does not help us uniquely distinguish each record or each row from each other is if you select GPA, multiple students can have the same GPA, right? Even though there is a uniqueness that you can see right here, but necessarily that won't be the case when you start to populate the table of all the students that are in the university, right? So same two students can have the same GPA. So that is not possible. Department will again not help us in that aspect because there can be multiple students belonging to the same department. The same goes for address as well, right? Name as well. You can have students having the same name, and even to a certain degree, the first name and the last name, right? So as you can notice here, what will be unique for all students is either the student ID or the student Grizzly ID. And to a certain degree, we can understand that having two IDs, Grizzly or otherwise, is kind of redundant, but it's just an example, so to begin, right? So we can either choose student ID to act as what is known as the unique identifier of this particular table, or sometimes, or most of the times going ahead, once we understand the concept of functional dependency and keys, it will be known as the unique key of the table. And later on, it will actually transform and be called as the primary key, right? So we don't want to go into this right now without understanding what keys are and stuff like that. So for now, just understand that student ID can act as the unique identifier. And the purpose of the unique identifier is to uniquely identify each and every record that is present in a given table. Okay. So now that we have understood that, let us segue into the natural progression of what is a key, or the concept of keys within the relational model. Okay, so again, keys are basically an attribute or a set of attributes that can uniquely identify a row in a table and distinguish them from other rows. Okay, so that means if I want to rephrase this definition here, we can say that if you know the value of the unique identifier, which is your key, right? Then you can compute the values, compute or find out the values of the remaining attributes. In the table. Of course, when I say remaining attributes for that particular row, okay, not all the rows, because the attribute or the identifier is going to be for a specific row itself and not the entire table. Okay, so other than that, not just determining the values of the remaining non-key attributes, keys also help us in implementing the integrity rules. Okay, and we will shortly see what these integrity rules are and why they are important. Okay, but they are very, very necessary within the database environment in order to avoid the challenges that we faced in the file system domains. Okay, so the concept of keys or keys have been developed from the concept of determination. Okay, so it's a math concept. So let's talk about that mathematical concept first. So the concept of determination and that of functional dependency. So this is a very important topic. Okay, make sure you understand this very well, because most of us have a tough time grasping this concept, because once you understand this concept, it will be very easy to deal with the mostly very frequently occurring terms of what is a primary key, what is a candidate key, what is a super key, what is a foreign key, so on and so forth. So if you understand the concept, the implementation of the concept becomes much easier to grasp. So you don't have, or you won't be required to kind of memorize what is happening there. You don't have to do that, right? So our emphasis should always be about understanding. If we understand, we will retain it for a longer period of time. Okay. So what the concept of determination states, determination. Okay. So what this state is that the state, or it says that if you know the value of an attribute or set of attributes, then you are able to know the values of the remaining attributes. Okay. So this is basically what we have. So that means that if we know, as an example from the previous slide, if we know the value of student number, then we can know the values of student GPA and let's say student address associated with that student number. So you see this relationship, this structure is basically based on the relationship between attributes. Okay. And this kind of determination, which is based on the relationship between attributes, this is known as functional dependency. Okay. So that means where is my cursor? Here. Functional dependence. Okay. So what functional dependence states that if the value of one or more attributes determines the value of one or more other attributes, then the relationship is defined as functional dependence. Okay, so in our running example that we had here, where did it go? This student number functionally determines the value of student GPA, comma, student address. So of course, student number can functionally determine every other attribute in that particular table. So we're just specifying a specific example, a small excerpt of the complete functional dependency that can be present here. So here, in this particular relation, this part is known as the determinant, and this part of the relation is known as the dependent. Okay. So now, of course, you can have many different forms of functional dependence within a particular table, right? So this particular example, again, can be rewritten as student number can determine student name, student GPA, student address, and then student department. So this is also an example of functional dependence, right? Again, student number and student name can functionally determine the value of student GPA. Okay, so this is also an example of functional dependence within the table. Okay, so you have to keep in mind. So now what we are getting towards is that in a functional dependency, in a functional dependency, if you remove some attributes from the determinant part and functional dependency no longer holds, then that functional dependency is known as a full functional dependency. Okay, so this is basically the definition, or a rephrased definition, of full functional dependency. So that means in that example where you had student number comma student name, determining the value of, let's say, student GPA. So now here in this particular functional dependency, if I remove some of the attributes of the determinant part, so there is a typo here, so just please keep in mind. Okay, so if I remove student name, right, I will still be able to make this functional dependency work, because still knowing the value of student number, I can determine the value of student GPA. So that means this particular relation is not a full functional dependency, or I'm simply going to call it FFD, where FFD stands for full functional dependency. Okay, but now if you remove student number, you are no longer able to determine the value of student GPA anymore. So at this point, this particular relation where student number determines the value of student GPA is a full functional dependency. Okay, and now you might have had the question that, okay, you removed student name here and this still worked, so it is not a full functional dependency. What about if I remove student number? Well, if you remove student number here, then student name is no longer unique. So if a determinant is not unique, then it won't be able to determine the value of the remaining other attributes. And as a result of that, if instead of removing student name, if you remove student number and retain student name, you wouldn't have a functional dependency anymore. You will lose the aspect of functional dependency altogether. So you have to keep in mind that regardless whether it is a functional dependency or a full functional dependency, a determinant must be or must have a unique value in the table. This is very important. Okay. So another way of stating full functional dependency would be the entire collection of attributes in the determinant side are necessary for the functional dependency to hold. Okay. So now based on this, we will establish or developing the concept of table keys. We generally don't say table as such, so we simply just say keys using functional dependency and full functional dependency. Okay. So first we are going to just simply talk about the different types of keys that we can generate. Okay. So the first one, so I'm just going to talk about the full hierarchy of different keys that you can have. So the first key that you can have is a super key. Okay. From a super key, what we can derive is known as a candidate key. Then from a candidate key, you can derive what is known as a primary key. Separate from this particular tree structure are the concepts of foreign key, which is a type of, let's not say that, that will confuse you. Let's just stay at foreign key. And then there is another one, which is known as secondary key. Okay. And then there are, now don't get confused with this one. If you see this composite key, okay, this is not actually a key. Okay, what that means is like it is not a concept, it is a term. A term to indicate that if a key is composed of more than one attribute, then that is a composite key, that it is composed of multiple attributes to form that particular key. So that means here, in this example, student number, comma, student name is a composite key, but that has nothing to do with the concept of determination, right? So this is just like a quick note rather than an actual concept. But please do not confuse yourself. The actual tree hierarchy, which is being developed using the mathematical concepts of functional dependency and full functional dependency, is restricted to the super key, the candidate key, and the primary key. And an extension of those three concepts is embedded within the foreign key and then the secondary key. Okay, I actually don't know how they represent a secondary key because you encounter it very less frequently in the implementation purposes. Not conceptually, you encounter it very less frequently. Okay. So I'll just quickly go over the concepts now, one by one, and relate that to functional dependency. So any key is a super key if it abides by the concept of functional dependency. Any key is a candidate key that abides by the concept of full functional dependency. A primary key is basically a candidate key selected to represent the table or uniquely identify all the rows. So based on this concept, that gives you an idea that there can be multiple candidate keys, but there only will be only one primary key. Okay. And then secondary key, a foreign key, are basically primary key of one table present in another table. And then secondary keys are keys which are designed or developed, or let's just call it generated, for data retrieval purposes. And as a result of that, they might not return unique rows. Okay. However, the super key, the candidate key, the primary key, and the foreign key will always return unique rows. So now at this point of time, if you have a good grasp of functional dependency and full functional dependency and how they are based on the concept of determination, then you should be able to follow this structure here. Okay. So as a result of that, if you take a few examples and talk about the different keys that we can have in a table, then let's look at a few examples. Okay. So keys and examples. Okay. So let's say if we have a relational notation for a table. So basically, if you want to represent a table in its relational notation without having to draw out the entire table, then you simply write it as such. You have the entity name, student, and then you have the opening and closing first brackets, and then you can fill out all the different attributes that you have separated by commas, right? So you can have student ID, let's say student first name, student initials, okay, student last name, and then let's say student address, thereafter student phone number, student GPA, student department, student designation or year, so that means will it be junior, senior, freshman, sophomore, so on and so forth. And then what else can we add? Can we add anything else? Let's leave it at this. Okay. And thereafter, of course, you will have to underline the primary key of the table. But since we are discussing about the examples, well, since we're just discussing the examples of keys, we won't underline anything as first. Okay. So first, let's look at some examples of super keys. Okay. So remember, super keys conceptually is any key. It could be an attribute or a set of attributes, okay, that abides by the concept of functional dependency. And the concept of functional dependency states that in the determinant side, if you know the values of those attributes, then you will be able to determine the remaining values in the table, okay, of the other attributes, right? So now here, the first and foremost is, and they have to be unique, right? So if you know the student ID, you can determine the rest of the attributes. Okay, so that means student ID is an example of a super key. Similarly, if you know a student's first name, last name, and then student initial, along with student phone number, then you will be able to determine remainder of attributes in the table, right? So that means this whole key, which is a composite key, is actually a super key because it is able to uniquely identify all the tables. Similarly, if I do student ID, comma, student first name, then it will also be able to determine remainder of attributes. Okay, so then this is also an example of a super key, right? Now if we look at the next example, which is example of candidate key, and so on and so forth, you can get the idea. You can create a combination of different attributes in order to ensure that functional dependency is met, right? So an example of a candidate key based on our concept tree is something that abides by the concept of full functional dependency. And full functional dependency states that here, that the entire collection of attributes in the determinant are necessary. They have to be present. If you remove them, then functional dependency no longer holds. Okay. So that means here, student ID determining the rest of the attributes is also an example of not just functional dependency, but full functional dependency. Because if you remove student ID, then this determination relationship breaks down, right? So an example would be student ID determining the rest of the attributes. But here, if you look at this example, if I again remove functional or first name, then you can still determine the remainder of the attributes, right? So as a result of that, the composite key of student ID, comma, student first name is not a candidate key because it does not abide by the concept of full functional dependency. You don't need all the attributes in the determinant side. However, if you look at this, student first name, last name, student initials, and student phone number, if you remove any one of the attributes, then you won't be able to uniquely identify the remainder of the attributes and distinguish them from each other. The unique part is important, right? So that means this one here, that is student first name, student last name, student initials, and then student phone number is also an example of candidate key. Okay. All right. So now if we look at the next one, which is example of primary key. So based on our concept tree again, we say a candidate key which is selected to represent the table. That is all the tabular operations or the relational table operations that we are going to be doing, which relies on uniquely identifying and distinguishing a row from each other, will require a key, right? So that key is going to be a candidate key. So if we have multiple candidate keys, then the one that we select to act as the key that is going to represent all the operations or the unique operations of the table is known as the primary key. So here, there are certain properties of primary key that helps you or aids you in identifying the selection of a candidate key, of a primary key from multiple candidate keys, right? So for now, let us just assume that if we select student ID to be the key or the unique identifier of the table, then student ID is the primary key. Remember, all primary keys are basically candidate keys. Okay. All candidate keys are basically super keys, but not all super keys are candidate key. Okay. So that is a distinction that you have to remember. So what you have to remember, so it's a small remark that you have to keep in mind, is that all primary key or PKs are candidate keys, and all candidate keys are super keys, but all super keys are not candidate keys. However, they all can uniquely identify rows of a table, let's say a relational table, from each other. Okay. So after that, we have the concept of foreign key, which based on the concept tree we have here states that it is a primary key of one table present in another table. So basically, foreign keys, so this is another remark, but this time on the foreign keys, is used to implement, and this is the important keyword here, the relationship, or we can also call it our interaction of data between two entities. So now recall the different types of relationship that we were discussing. So we were talking about 1:m, and then we had this relationship where the professor, so if we use the crow's foot notation here, so the professor advises multiple student. Okay, so let's say we had this, and then we had this, okay, and advices. So now here, if the primary key of professor is, let's say, an employee ID, then along with all these attributes that uniquely identify or describes a particular row in the student table. So if the primary key of the student table, as we identified, was student ID, then in addition to that, the student table will have a foreign key, which will be employee ID. And this employee ID is basically the primary key of another table, but the foreign key in the table of student ID. So in addition to this, we will have a different attribute that is not a part of this table as such, but it is coming from another table, and it will be something along the lines of professor ID in order to establish a particular relationship, and that is a foreign key of that particular table. Okay, so that is what the idea of a foreign key is, or the concept of a foreign key. So the final thing that remains is the secondary key, which is keys that are developed to simplify the data retrieval process. So let's say me as a professor, I want to find a particular student from the student table, right? So now, of course, we have set up all these conceptual keys, which are very good at distinguishing a row from each other. That is the student ID being the unique identifier, right? So, but when I, as an end user, I'm interacting with your interface, And if your search field only kind of enables me to enter a student ID, you have to ask yourself this question: as far as design principles are concerned, would it be a good idea to just allow the user to be able to enter a string of numerical values which are unique from each other? It is not practically feasible. That is not a good design principle, right? So if we are searching for data, we must have keys or search fields that are user-friendly. So any set of attributes, any attribute or any set of attributes that helps us simplify this process of retrieving the data is a secondary key. So, and as a result of that, there is no uniqueness in the results that might be returned. So some examples, what was this? So some examples of secondary keys would be basically, let's say, student GPA. So if I simply write GPA greater than 3.5, then it can give me the list of all students, right? I can have student address. I want to find all the students who are living closer to the university, right? So if the address can be broken down further into state, city, zip code, so I can provide the zip code of students who are from this state, closer to the university, outside. I can even provide something like a student first name or a combination of any of these attributes, right? So remember, the goal is to make the process of searching data and retrieving it as user-friendly as possible. So as a result of that, any key or any set of attributes or any single attribute that helps us in that purpose will serve as a secondary key. So you can have multiple secondary keys for a given table as well. But remember, do not confuse secondary key with the mathematical concepts of primary keys, candidate keys, and then super keys, okay? So they are mostly mathematical concepts, and internally the operations of database are guided by them, right? But beyond that, secondary key, it's only for a front end purpose, okay? All right. So thereafter, the final topic of part one of this lecture video are integrity rules, okay, which helps us preserve the integrity and accuracy of stored data, okay, and they depend on the concepts of keys, of database keys, okay. So there are two different integrity rules. The first one is known as entity integrity rule, and then the second one is known as referential integrity rule, okay. So we will discuss this after the entity integrity rule, so let's not go there, just keep it clean for now, okay. So what does the entity integrity rule say? It states that each row in a table has its own unique identity. That is, no two rows are similar. And in order to enforce this, what you have to ensure that all values of primary key attribute are unique and no attribute or no attribute value of the primary key can be null. Okay. So these two expressions are basically very important. Okay. You have to make sure that all the values, there are no duplicate values in the attribute that you select as a primary key, and none of them can be empty. Okay. So that means if I selected student ID as my primary key for the students table, so that means no two student ID are the same, and there isn't a single student who has not been assigned a student ID. So this requirement must be enforced in our database design. Okay, so this has to be there. So in some cases, there might be situations that null values cannot be avoided as such. Okay, so keep in mind that then you can provide certain flags or certain ways in which you can evaluate whether it is null or not. But let's not go there. Always keep in mind that select a primary key which has unique values and which cannot be null. Always keep this in mind. Okay, this is quite essential. There are ways when you're going to implement your table to ensure that whichever column is going to be your primary key, that they are unique and they are not null. Okay, so when we get to SQL, we'll discuss more about that. And the second integrity rule is basically the referential integrity rule. So the referential integrity rule states that every reference if there is a relationship between two entities, could be two or more as well, but let's just say two entities, then every reference from one row or from the entity instance of one table to another must be valid or null. Okay, it must not refer to some repeating instances. All right, so this is enforced by the foreign key. Okay, so that means if I want to rephrase this definition, every value of the foreign key attribute must either refer to a valid primary key instance of the parent table because the foreign key is a primary key of another table, or it should be null. And what this means is that necessarily not all entity instance, that is not all row, will be related or associated or will have a relationship to the rows of the other entity, right? So what that means that there might be a possibility, given the organizational policies, that not every student has an advisor in the form of a professor. They can have some staff members in the advising office as their advisors, right? So that means when we are implementing this situation here, in this particular case, some of the students might have this value as null, which is not a problem because that is only kind of expressing that that particular student doesn't have any professor as their advisor, and that is about it. So that is the reason the foreign key referential integrity rule states that every foreign key attribute must refer to a valid primary key instance or be null, whereas the entity integrity rule is enforcing the fact that all the values of the primary key need to be unique and no attribute should be null. Okay, so these are the two integrity rules that must be enforced within any database design that you develop, right? So please make sure that you keep that in mind, okay, and familiarize yourself with it. So this concludes the first part of this video, right? So in the next one, we will discuss about the relational operators in the relational data model. So I will see you all again in the second part of this lecture series or of this lecture video. Until then, stay safe and take care.